My name is Marcelo Fonseca Faraj. It is a pleasure to be presenting a work at SCA 2020. The title of this work is High Quality Hierarchical Process Mapping. Let's assume a parallel algorithm for an HPC or high performance computing system. We can see this algorithm as a set of processes in which each process is at the same time atomic, has a computational cost, and can exchange messages with other processes. This induces a communication graph G. In this communication graph, we have n nodes, which are also the number of processes. Each vertex or node V represents a process V. Each vertex weight C of V represents the duration of the corresponding process V. Each edge VU represents the existence of a message between processes V and U, and the edge weight CVU represents the message size. An HPC system can be seen as k processing elements contained in some topology. And in our case, let's assume that the processing elements considered have all the same power and that this topology is a hierarchy. So let's define the matrix D, which is the distance matrix in which an element Dij of this matrix represents the distance between the processing elements I and J. And let's define two vectors, A and B, in which the vector A represents the submodule bilevel structure of this regular hierarchical system, and B represents the cost bilevel structure of it. Let's give an example. A1 would represent the number of processors by chips, A2 would represent the number of chips by compute cards, and so on. In the case of the vector B, D1 would represent the communication cost between two processors inside the same chip. D2 would represent the communication cost of two processors in different chips but in the same compute card, and so on and so forth. Now that we've defined both the communication graph and the hierarchical topology, let's define the general process mapping problem. It consists basically of obtaining a map pi from each node of this communication graph to a processing element of this hierarchical topology. This mapping has to respect a constraint which is named balancing constraint, and this constraint establishes similar workloads for each processing element. For example, we could say that we allow an imbalance of at most 3% or 1%, and we have to do this mapping in order to minimize a function which we call total communication cost, and it is defined as J. J consists of the total communication between two processing elements multiplied by the distance between these processing elements. Now let's go into the solution approaches, and the most common solution approaches for general process mapping problem are the two-phase approach and the integrated approach. The two-phase approach consists of you have a graph and then you partition this graph obtaining k virtual blocks. And then in these k virtual blocks you apply a one-to-one mapping algorithm, and then finally you obtain a physical map from the original graph to the processing elements. Observe that this two-phase approach is intrinsically not exact, because if you solve the partitioning to the optimality and then you solve the one-to-one mapping also to the optimality, you don't have any guarantee that the global general mapping problem will be solved to optimality. The other approach, on the other hand, is called the integrated approach, and in this case you have the original communication graph and you go directly from this input to a physical map to the processing elements. Let's take a closer look at these three problems: partitioning, one-to-one mapping, and general mapping. As this picture here shows, partitioning and one-to-one mapping are special cases of the general mapping problem. Because for partitioning, it is simply a general mapping problem with a single layer and in which the number of nodes in the communication graph is larger than the number of processing elements. And in the case of the one-to-one mapping, it is simply a general mapping with multi-layers in which the number of nodes in the communication graph is equal to the number of processing elements. These three problems are NP hard, so they are only solvable heuristically for large instances. Now I will show some literature remarks about the general process mapping problem. It is a fundamental problem for parallel computing and distributed computing. However, it has not yet been satisfactorily solved in practice. although literature works include different formats, different aspects, different approaches, and different formulations. This problem is usually tackled as a static problem. Now let's give a closer look to the state of the art of general process mapping problem. We have actually two states of the art. In the first one, we consider the integrated approaches to solve GPMP. We include two solvers in this case. Scotch, it consists of a multi-level scheme using some fiducia mataesis local searches, and Jostle. However, Jostle is currently retired. In the case of the two-phase approaches, in the literature, it is very usual to use the K-heap algorithm followed by some mapping algorithm. And for the mapping algorithm, the most common approaches are these four listed here. First, the identity approach. Identity basically consists of assigning each virtual block to the physical block with the same identity as it. It is good because K-heap, while executing, keeps locality. Top-down N is an algorithm to partition the virtual blocks in a top-down fashion throughout its hierarchy. So, for example, we first partition these virtual blocks among the different computing units, and then for each computing unit, we partition the assigned data to the corresponding submodules. It goes down until each virtual block is assigned to a physical block. In the case of Müller-Mehrbar, it is included in this list not because it is particularly fast or effective, but because it has been considered in other works as a reference perspective for solution quality. And the global multi-section, which is the current state of the art regarding solution quality, it is not simply a mapping approach. Actually, in the global multi-section, the partitioning step already performs a partitioning throughout the hierarchy in a top-down fashion, exactly as the top-down N algorithm does. And then, after the graph is partitioned, there is a second step in which the virtual blocks are assigned to physical blocks. And in the second step, a top-down N algorithm is used. And now I will show our contribution. Here you can see a picture detailing our multi-level scheme. First, you have an input graph. You find matchings in this input graph and contract the edges contained in this matching. And it continues over and over until we can apply some expensive initial mapping algorithm. After we apply the initial mapping algorithm, we uncontract. And every time we perform an uncontraction, we also run a battery of local search algorithms to improve the solution quality even further. And we do this until we obtain again the initial graph and we already have a mapping with high quality. Let's make some definitions. First, a match M is a subset of the edges of a graph in which there is no edge sharing endpoints. In other words, it means that if we consider a graph containing the same vertices as the original graph and only the edges contained in the matching, this will be a graph with no node with degree higher than 1. Second definition, a matching is considered maximal if and only if no edge can be added to the matching. We show here down below two matches. The match in the left is not maximal since we could add one more edge to this matching and this will continue being a match. On the other hand, the match on the right side is a maximal matching since we cannot add any more edge to this match. Third definition, the weight of a match is the sum of the weight of the edges contained in this match. And fourth definition, a maximum matching is a matching that has the maximum possible weight among all matchings for a given graph. The second thing we should observe is that how we actually do the contraction. Let's look, for example, at this graph and consider a match containing these two red edges. The contraction consists basically of, for each edge of the match, you remove its two endpoints and substitute them by a single node. And the weight of this new node will be the sum of the weights of the two nodes removed. And the edge between this new node and the neighbors of the removed two nodes are compressed in a single edge to each specific neighbor in which the weights of the previous edges are summed when necessary. Let's imagine that the nodes A and B were in one partition and their neighbors were in another partition. In this case, after the contraction, the edge cut is maintained. Since we maintain the edge cut, we also maintain the communication cost of the mapping. Now let's look at our initial mapping algorithms. Our initial mapping is a two-phase process. If you well remember, we said that our method is an integrated method. The detail is that our initial mapping algorithm, the algorithm that we apply to the coarses version of the graph, is a two-phase process. We take a graph, we partition it into k virtual blocks, and then we map these k virtual blocks in a one-to-one mapping to the physical processing elements. For the partitioning, we consider two possible algorithms, the recursive bisections and the multi-sections. And for the one-to-one mapping, we also consider two possible algorithms, the top-down N and the identity algorithm. We have already explained both, describing the state of the art. About the recursive bisections, you have the whole graph, you do a bipartition in it, obtaining two graphs, and for each of these two graphs, you again do a bipartitioning and repeat this recursively over and over until you have the correct number of partitions. This method works in a natural way when the total number of processing elements is a power of 2. However, when the total number of processing elements is not a power of 2, this initial partitioning method can generate unbalanced blocks, in which we will have to apply further algorithms to obtain balanced blocks. The other approach is called multi-sections. Multi-section is more adapted to the case in which the number of processing elements is not a power of 2. We have an example. We have this hierarchy: 2 chips by compute card, 2 compute cards by node, and 3 nodes in total. We first take the whole communication graph, so we partition them in 3 parts. Each of these parts defines a graph, and then for the graph representing each node, we partition it into 2 compute cards. And then for the graph representing each compute card, we partition it into 2 chips. It can apply more naturally to any hierarchical configuration. Using these components, we construct 6 different initial mapping algorithms. In the first 2 algorithms, we apply the bisection and the identity and the top-down N algorithms, depending on whether the number of processing elements is a power of 2 or not. In the following 2 initial mapping configurations, we use the multi-section followed by the top-down N algorithm. And in the last 2 configurations for initial mapping algorithm, we use the multi-section for the partitioning and then the identity algorithm for the assignment. This is particularly good because this multi-section algorithm, as well as the bisection algorithm, has a very good locality. After computing an initial mapping for the most contracted version of the graph, we apply a sequence of local refinement methods during the uncontraction step, as I already mentioned. For each local search, we use the concept of potential gain of moving a node from its current processing element into another one, based on the minimization of the total communication cost. In particular, we have implemented 4 local search algorithms, which are illustrated here. In the first one, the quotient graph local search, we apply a fiducia-Mathesis refinement for each pair of processing elements sharing at least one edge in the current mapping. In the k-way FM, on the other hand, we do not restrict the movements of nodes to specific pairs of processing elements. Rather, it is a global adaptation of fiducia-Mathesis in which a visited node can move to any processing element containing at least one of its neighbors. The third local search is simply a label propagation in which no movements of nodes can increase the communication cost. And finally, the fourth refinement is called multi-try FM. It is a variant of the k-way FM with repeated reinitializations in random boundary nodes. It can escape local optima better than k-way FM since it restarts over and over. The last components of our algorithms are techniques to improve the overall performance. The first one is known as delta gain updates. Roughly speaking, it consists of storing the potential partial gains associated with each node throughout the whole algorithm. The objective of using delta gain updates is to avoid recomputation, and the cost is O of m plus n extra memory. The second performance technique we implemented is the implicit representation of the distance matrix D. I will now give more details about 4 different approaches we used to represent the distance matrix. The simplest and most straightforward approach consists simply of storing the whole distance matrix. An immediate advantage of this method is the O of 1 time to access a distance between 2 processing elements. Nevertheless, it requires O of k squared memory space, which may be too much when k is large. On the other extreme, we have the division approach, in which no memory at all is necessary. Particularly, the processing elements are orderly labeled according to their positions in the topology tree. Thus, we can compute the distance between 2 processing elements by successively dividing their labels by the number of submodules in each level of the hierarchical topology. By doing so, we find the closest common module shared by both processing elements, which implies a corresponding communication distance. However, this method requires O of L divisions and O of L comparisons, in which L is the number of layers in the topology. To speed this up, we implement the stored division approach. It works basically the same way as the division approach, but the results of all possible divisions for the label of each processing element are pre-computed once and then stored. This representation requires O of KL extra memory, but only O of L comparisons to compute a particular distance. Our fourth approach is the binary notation, in which we compact the stored division as much as possible in order to keep simply a bit array for each processing element. To obtain the distance between 2 processing elements, we simply perform an XOR operation between their bit arrays and find the leftmost non-zero in the result, which implies the closest common module shared by both. Theoretically, this representation requires O of k memory and O of log L time to compute the distance. However, current processors often implement a count leading zeros operation in hardware. This basically means our running time in practice is simply O of 1. Now, let's go to the experimental evaluation of our algorithms, and we do these experimental evaluations in 2 steps. The first step is named parameter tuning, and we use these graphs listed here for the parameter tuning. The number of processing elements used are 64 times x, in which x goes from 1 to 128. The topology used consists of a vector A equals to 4 by 16 by x. The vector B is simply 1, 10, and 100. For each instance, we do 10 repetitions with different random seeds, and we do geometric mean grouped by algorithm and k. We produce 4 versions of our algorithm. The first version is named strong, and in this version we only care about making solution quality as high as possible. On the other extreme, we have the fastest version, in which we only care about making our algorithm as fast as possible. In the middle, we have intermediary versions. In the equal version, we care more about quality than running time, and in the fast version, we care more about running time than quality, but both are in the middle. Regarding the initial mapping algorithm, this chart shows the solution improvement compared to the most basic version of the initial mapping algorithm. In this graph, the x-axis is the number of partitions and the y-axis is the percentage improvement over the bisection initial mapping algorithm. Higher means better. Observe that the best algorithm regarding solution quality is the green one. This makes this algorithm the natural choice for the strong version of our algorithm. For the other versions, we have to look at performance profile of these initial mappings. But observe that the second best algorithm is the blue one. And now let's look at the time profiles. To build a performance profile chart, for each value of k, we normalize the average runtime such that the slowest algorithm is assigned 1. Then for each algorithm, we plot these normalized runtimes in ascending order. The green one is not the fastest algorithm. However, the blue algorithm is the fastest one, and at the same time it is the second best regarding solution quality. So it is our choice for the other 3 versions of our algorithm. Due to time constraints, it will not be possible to show all our experiments for local refinement. However, I will show one of them to exemplify how the tuning process worked. This graph shows solution quality improvement over a scenario in which only the quotient graph local search is used. Higher means better. Observe that the version with all local searches is the best one. Solution quality gets worse as we consecutively remove local searches. And here in this slide, we show the local searches included in each version of our algorithm alongside with their relative execution orders. Observe that the strong version uses the 4 local searches, the equal versions uses all local searches but 1, the fast version uses simply label propagation, and the fastest version uses no local search at all. In here, you can see the performance plot for each of the 4 approaches for the implicit representation of the distance matrix. Lower means better. Interestingly, the binary notation approach performs better than all the other approaches, even the full matrix. This happens because there is a memory delay to obtain a distance using the full matrix approach. With our algorithms tuned, we use a new set of benchmark graphs for the comparison with the state of the art. And you can see here the list of graphs used for the comparison with the state of the art. Here we show percentage improvement over the Müller-Meerbar algorithm of all the state-of-the-art algorithms and our 4 algorithms, which are listed in the middle column of the caption. Our 3 algorithms with best solution quality, the strong in blue, the echo in green, and the fast in purple, are very well located at the top of the graph. Observe that the only algorithm which seems better than these 3 algorithms is the global multisection in its strong version, represented in brown. Also, take a look at the Scotch algorithm, represented in the 3rd column of the caption, and displayed in pink. It is better than only 2 algorithms regarding solution quality. On the other hand, look at the fastest version of our algorithm represented in red triangles. Although it is not among the best algorithms, it is certainly much better than Scotch. Now let's look at the performance profile time for the same algorithms. Each algorithm in this chart is represented with the same color it was represented in the previous chart. Look at the strong version of our algorithm in blue and observe that it is far from being the slowest algorithm. And now look at global multisection algorithm in its strong version in brown. It is much slower than the strong version of our algorithm. Now take a look at Scotch. Scotch is overall the fastest algorithm. However, our fastest algorithm, represented in red triangles, is almost as fast as Scotch. In particular, it is only 9% slower than Scotch on average. In summarizing, we engineered all the components of a multi-level integrated mapping algorithm. We did a lot of experiments to tune our algorithms and then to compare with the state of the art. And we come to the conclusion that our algorithms become the new state of the art. In particular, the strong version of our algorithm is, on average, as good and an order of magnitude faster than the previous best algorithm. The echo version of our algorithm is 2.4% better and 2.8 times faster than the previous second best algorithm. The fast version of our algorithm is better than all the other algorithms except the 2 previous best algorithms. At the same time, this fast version is faster than all the other algorithms except the 2 previous fastest algorithms. And finally, the fastest version of our algorithm is as time efficient as the previous fastest algorithm, namely Scotch, and on average 16% better than it regarding solution quality. The 4 versions of our algorithm will soon be available in Kahip and in Vienna mapping. In future work, we intend to work with parallel and distributed algorithms for general process mapping problem, and here I list our 3 funding sources. Thanks for watching this talk. If you need anything, please email me at marcelo.fonseca-faraj@univi.ac.at.